Good morning. Let's talk about the Lab 8 equilibrium issues with what to draw and how to solve for our knowns. So in part 1, after you have found the center of mass of the meter stick, we're asked to put the fulcrum at the 20 centimeter mark, or 0.2 meters. Suppose that the center of gravity location was 50 centimeters. We have the weight of the meter stick. I'm subscripting CG as center of gravity, and force due at the center of gravity, the mass of the meter stick times gravity. In order to find the torque exerted here at the center of gravity, we have to know the lever arm for the center of gravity. To do that, we must subtract 20 centimeters from 50 centimeters. That means the lever arm for the center of gravity, let me write this down, 50 centimeters minus 20 centimeters is 30 centimeters, or 0.3 meters. The lever arm is simply the distance between the position of the mass and the fulcrum. The torque exerted will then be the center of gravity's lever arm times the weight of the meter stick. Not knowing what the weight of the meter stick is, you can fill in for your particular meter stick, but we'd have 0.3 meters. Let's suppose that it was a 60 gram. That would be 0.06 kilograms, moving the decimal 3 places, times gravity. That would mean that the center of gravity's torque, grabbing a calculator, 0.3 times 0.06 times 9.8, and the kilogram meters per second squared will give newtons, and then we will have meters. So 0.176, rounding to 3 decimal places, meter newtons. Now the question is, where on the left side will a mass have to be? I'm drawing it not to scale, but I'm going to say force of, say, a 200 gram mass. We want to know what the lever arm needs to be. And since there are only 2 torques here, one on the right side of the fulcrum and one on the left side of the fulcrum, in order for the meter stick to be in balance, we must have the torques being equal. That means that the torque for the 200 gram mass must equal the torque for the center of gravity, which, for my made up numbers over here, 0.176 meter newtons. The good news is we know what the force due to gravity of the 200 gram mass is. So F200 is 0.2 kilograms. 200 grams is 0.2 kilograms. Multiply that by 9.8 meters per second squared, and we get that that is 1.96 newtons. Now, I would like to add, that is the force of a 200 gram mass. Know that this mass actually includes the hanger. So if you are using a 200 gram mass, for instance, the actual mass here is going to be greater than 0.2 of a kilogram because you have to add the mass of the hanger. I'm just showing you example calculations. I'm assuming the 200 grams here actually contains the mass of the hanger. So what we have here is a linear equation similar to the first one we worked out in lab, where we have 1.96 newtons times the lever arm must equal the torque for the center of gravity, which we know is 0.176 meter newtons. So we divide both sides by 1.96 newtons to arrive at the lever arm must be 0.176 divided by 1.96. The lever arm, and I'm going to round this to the thousandths of meter because we can go to the millimeter. 0.0897 rounding here. At the third decimal place, 0.090, which is 9 centimeters. That means that is the lever arm. So the location is the 11 centimeter mark. So this value here, the 9 centimeters, this lever arm, that is the observed. So the observed lever arm, 9 centimeters. I'm converting back and forth between meters and centimeters. Excuse me, that's not observed. That is, let me back up, that is not observed. That is what we calculated it to be. This is where you expect it to be. We expect this mass to have to be at the 11 centimeter mark, which would be 9 centimeters away from the fulcrum. So that is the expected. The observed is where you actually had to put it to get it to balance. So for the relative error calculation for this part, suppose, and I'm making this number up, suppose you had a 10 centimeter observed lever arm, meaning the mass was hanging at the 10 centimeter mark, 10 centimeters away from the fulcrum. So the relative error would be the observed 10 centimeters minus expected divided by expected times 100 to get into a percent. So 10 centimeters minus 9 centimeters is 1 centimeter. We divide that by 9 centimeters. Ultimately, we can use centimeters or meters here as long as we are using the same unit for both measures. We multiply this by 100 and we get that the relative error would be 11.11